Okay, so what three things affect EMF induced in a wire and why? So we just talked about them in the lab. And the three things are magnetic flux, okay, number of loops, and I think maybe a way to explain this last one a little easier is time to change field. Okay? Because in the first part of this notes, we said what electromagnetic induction was, is it was a changing magnetic field to cause a voltage. So this is the time it takes to change that. Okay? So those are the three things. So the question then is, how do these things matter? Or why do these things matter? So what I want you to do is, thinking about the example or the lab we just did, I want you to take a minute and write down why you think these things matter. Why do you think the amount of magnetic field through a wire matters? Why do you think that's important? Why do you think the number of loops matter? And why do you think the time to change the field matters? So there's no trick ones here. It's not like, you thought it did matter, but it doesn't. So magnetic flux matters because the more field you have going through, the more you're going to cause a EMF because there's more stuff happening. The number of loops matters because this change happens through every single loop. So if you have 100 loops, it happens 100 times over. If you only have 10 loops, it only happens 10 times over. And the time to change the field makes the effect happen quicker. It happens more dramatically. So here we go. Faraday's law. So let me give you the basic version, and then I'll give you the actual version. So here's the basic version. The basic version is EMF. Now there is a symbol for EMF. It's like an alternative version of sigma, and it kind of confuses people. So I just write EMF. EMF is approximately, again, this is just the bare bones. Here's kind of what it is. It's approximately the number of loops times the magnetic flux, the change in flux, I should say, divided by the change in time, the time interval. So N is number of loops. Okay? N is the number of loops. This delta phi business, that weird thing, that is change in magnetic flux. And delta t is the time interval for the change. Okay? Okay. So that's the basic version. And the reason I wanted to show you to it is I wanted you to see, hey, look, you've literally done all this stuff in the lab. Number of loops, change in the flux through the wire, the time it takes to do all that change that you do. So now let's put the full equation together so you can see what it really is. And then we'll talk about how that is different. So here's the full equation. EMF equals negative N A delta B over delta T. So first of all, N is still the number of loops. A is area. And what I mean by area is the area of the loop. Delta B is change in magnetic field. And delta T is still time interval. So let's talk about where all these things come from. There's N. There's delta T. And remember, we said delta phi is the change in the flux, and flux is how much field goes through a loop of wire. Here's the loop of wire, and there's the field. So I just broke flux down into the parts that matter for our size amount. The things that we talked about in the lab, these things are affecting direction, which we will come to a little bit later. Because as you kind of notice, this unit's kind of picky on directions. But here it is, there's Faraday's law. Questions on what it is? Nice. Okay. Let's do just a little bit more here. Yeah, just a little bit more. Let's do 6 through... 6 through 7?
Yes.
I can do that. It's because you got lucky and 8's a completely different topic.
Oh.
All right, so number 6. If a voltage is induced in the wire, then what else is induced? Well, if you induce a voltage, you have to induce a current. Right? V equals IR. If you induce a voltage, an EMF, then there has to be a current in the wire. Okay? And if you induce a current in the wire, then what else has to be induced? A magnetic field. So here's what happens. I have a loop of wire. I get a magnet. A nice, bright pink magnet. Okay. That magnet creates field lines. Doop-a-doop-a-doo. Ba-doop-a-doop-a-doo. Ba-doop-a-doop-boo. Ba-doop-boo-boo-boo. There we go. Okay? So, when I put the magnet in, it creates an EMF. Okay? It creates an EMF. That EMF causes current to flow around the wire. Don't worry about the direction yet. And, as we've already talked in this unit, when current goes through a wire, what happens? It creates a magnetic field. So, oh snap, you use a magnetic field to create a magnetic field. I know. Lenz's law. So, obviously, direction's kind of been a thing this whole time. So, Lenz's law is part of Faraday's law. And you're probably saying to yourself, well, I didn't see any other part of this law. Where on earth could Lenz's law be? Well, here it is. Ready? Whoop. That's Lenz's law. Yep. Lenz's law is literally a negative sign. So Faraday came up with the thing, and then Lenz was like, oh, hey, it needs this. So that's his contribution to physics. So one day you guys can also contribute by putting a negative sign in someone else's equation.
E equals negative MC squared.
Snap. There you go.
Negative MC squared.
Yeah.
Wow.
No, you should make it negative MC parentheses negative C squared.
Yeah.
Because that technically is different, but it's not. So what is Lenz's law? So Lenz's law just states that the induced magnetic field is always opposite of the flux change. A good way to think about Lenz's law is that the induced field opposes what's being done to it. Okay? Lenz's law is like a 2-year-old. Whatever you tell it, it's like, no, I'm not doing that. I don't want it. Okay? So if you start giving it more field, Lenz's law, yep, will say, no, I don't want that. Lenz's law always says that the induced field will be opposite of what the change in flux is. So if the change in flux is in, the induced field is out. If the change in flux is out, then the induced field is in. They're always going to be opposites of each other. So how do we use this in our problems and stuff like that? We're not going to solve today. So I'm just going to kind of show you how to work your way through it. Okay? So the way that it works is you basically, you use it to figure out, here, I'll just say this. So it's used to figure out direction of current in the wire. All right. So here's my loop of wire. I'm going to take a magnet, and I'm going to put the magnet into the loop of wire. Okay? That's going to create a field into the loop. Lenz's law says that if the flux is in, then the induced field is out. So the field comes like this, outside of it. And now you might be saying to yourself, well, what does that tell me about the current? Well, the right-hand rule says that my fingers curl in the direction of the field, so they curl out of the loop, and my thumb goes in the direction of the current. And using Lenz's law, I can figure out that if the flux is in, the induced field is out, and the current goes counterclockwise in my loop. If the flux is out, I pull the magnet out of it. The flux is out. That means the induced field is in, and the current is clockwise around. So there you go. The right-hand rules and all that stuff that you learned, it actually all goes